Hello everyone, welcome to the next chemistry online class. In the last class, we were discussing about the first chapter, that is periodic table and periodic trends. So we have discussed many of the periodic trends. The first one was atomic size. The first one was actually nuclear charge, then atomic size, then a metallic atom, non-metallic atom, ionization energy, and the last one was electron gain enthalpy or electron affinity. So in the last class, at the end, we discussed a little bit about electron affinity. But if you are looking in the textbook, you can see some problems in that. So the trend that we are studying for electron affinity is this. Electron affinity, it is maximum on the right hand side. If you move from left to right, the electron affinity is supposed to be increased. On the left side it is minimum, and when we are going down a group, it is supposed to decrease, or in other words, electron affinity it is maximum on the left, on the right top side of the periodic table. So if you are looking into your textbook, you can see the electron affinity value. For example, here in the textbook, minus 73 for hydrogen, minus 60 for lithium, minus 53 for sodium. Okay, so actually when we are going down a group, electron affinity is supposed to be decreasing. Okay, but here you can see it is minus 73, minus 60, minus 53. Okay, so you can see it is actually not decreasing but increasing, right? Minus 53 is a larger value compared to minus 73. The problem here is this minus, it is not a normal minus sign. It is just a sign to indicate whether the energy is released or absorbed. Okay, for example, suppose an atom, it loses energy. So suppose the energy that it loses is E1, so it will be indicated as minus E1. Suppose that same atom or same electron gain energy, it will be indicated as plus E1. So this minus value, it must not be considered while looking for electron affinity. So even though there is a minus charge here, you don't have to consider that minus charge while looking for the periodic trend. So if you are just looking at the magnitude of the numbers, 73 is the highest. So if you are going down a group, electron affinity decreases. So in other words, in the textbook, there is a table of electron affinity. So when you are going through electron affinity, please make sure you don't have to consider the negative sign. You just check the value. If it is having maximum value, just consider that maximum negative value, just consider that as the highest value. Okay, so this electron affinity, it is having many confusions and problem because it is not a regular, it is not showing a perfect periodic trend because there are many exceptions. So I recommend you not to go beyond the syllabus about this topic, just electron affinity. Okay, so we are moving to the last periodic trend, that is electronegativity. Okay, so the last periodic trend, that is electronegativity, it is based on the ability of an atom to attract the bond pair of electron towards its side. So this is applicable only in a compound. For example, okay, So this is a hydrogen molecule. So the electron that is shared between both the hydrogen, it is placed on the center of the bond. Okay, so it means that two electron, it is not towards one hydrogen, it is not away from the same hydrogen. Okay, they are placed in, you can tell it like the bonded pair of electron, it is placed at the center. Okay, now this is the case of hydrogen. Suppose I am drawing in the case of HCl. I am just drawing the outer electrons of chlorine. Okay. The shaded electron in case of hydrogen, and the other 7 electron, it is the valence electron of chlorine. So actually in this case, the shared pair of electron in the single covalent bond between hydrogen and chlorine, it is supposed to be at the center of both the bond, but actually in the real case scenario it is not like so. So this chlorine, it is having high electronegativity compared to that of hydrogen. In other words, chlorine is having having more electronegativity, means it is having the power to attract the bonded pair of electron towards its side. Okay, so in other words, so if I am enlarging it, it will be likewise. Here is the hydrogen nucleus, here will be the chlorine nucleus. The bonded pair of electron, it will be moving towards the chlorine instead of moving towards the hydrogen. It will be moving away from the chlorine atom. Okay, so this is the case. So this kind of tendency, this tendency of an atom to attract the bonded pair of electron towards its side, it is called electronegativity. So those elements which are having high electronegativity, they will attract this bond pair of electron towards its nucleus or towards its center. Those which are having less electronegativity, they won't attract the bond pair of electron. In other words, the bond pair of electron, it will be moving away from them. Okay, so that is about electronegativity. Now we are going to discuss about the periodic trends in electronegativity. So this electronegativity, it is based the scale of electronegativity or the values of electronegativity of each element, it is based on Pauling scale. It is formed by a scientist called Linus Pauling. So based on his scale, all the values of electronegativity, it is already measured. So it is likewise, it is all the cases are similar to that of electron affinity. So maximum electronegativity, the element with maximum electronegativity, that is fluorine. The elements with minimum electronegativity, there are two, cesium and francium, both are having 0.7 value. The maximum electronegativity value of fluorine, it is 4. This can be asked for the board exam. It is a good question, so keep that in mind. Now, so electronegativity, it decreases when moving down a group. For example, just now I have told fluorine is having electronegativity 4. Below fluorine, it is chlorine, so it is having electronegativity 3. Now bromine, it will be having electronegativity 2.3, and it goes on. Okay, so in other words, if you are moving down a group, electronegativity decreases. So just now we have discussed the element which is having the highest electronegativity is fluorine, it is having electronegativity 4, and the lowest one, that is cesium and francium. So where does this cesium and francium slice in the periodic table? It is in the first group, bottommost. So here is our cesium. Below that we are having francium. It is having 0.7. Both of them are having 0.7 as electronegativity value. So if we go up in a periodic table, we are having the value will increase to 0.8 for rubidium, and if we reach up to hydrogen, it is 2.1. Okay, so if you just observe this, it is just the same case as the halogen group. If you are going down in a periodic table, again electronegativity decreases. So if you are moving from hydrogen over this side to the right hand side, the electronegativity it increases. So electronegativity it is maximum on the right top side, it is minimum on the left bottom side. So if you are moving from left to right in a periodic table, electronegativity increases. If you are moving down a periodic table, if you are moving down a group in a periodic table, electronegativity it decreases. Okay. You can explain this based on atomic size also. So you know that if you are moving from left to right in a periodic table, atomic size it is supposed to be decreased. So if the atomic size is decreased, that means electronegativity increases. Similarly, if you are going down a group, atomic size increases. So in other words, if atomic size increases, that means electronegativity it will decrease. Okay. Okay, now we will just summarize whatever we have learned in this chapter. So the first thing that we have discussed, it is about the nuclear charges. So we are going to discuss all the periodic trends here. So the first one, nuclear charge down a group. What happened to the nuclear charge if you are moving down a group? Actually nuclear charge it is supposed to be increasing. Okay. If you remember, when we were discussing about the atomic size, we told that down a group, nuclear charge it is increasing, but there is some other factors like a new shell is added. Because of that, there is some inter-electron repulsion between the inner and outermost shell electrons. So because of that reason, the atomic size is increasing. So I'll write that also here. Okay, so I hope you remember the conditions there. So due to even though nuclear charge is increasing, atomic size is also increasing. The reason is, even though nuclear charge is increasing, the other factor, that is in the electron repulsion or effect of having a new shell, it dominates over the nuclear charge. You are supposed to write as such. Now, in case of when we are moving across a period, again nuclear charge increases. What is the reason why nuclear charge is increasing when we are moving down a group and across a period? The reason is because the atomic number it is increasing. Atomic number increases means what? The number of protons inside the nucleus is increasing, or the positive charge inside the nucleus is increasing. So definitely it will increase the nuclear charge. So we have discussed the atomic size when we are moving down a group. What happened to the atomic size when we are moving from left to right in a periodic table, or across a period in a periodic table? So while we are moving from left to right, it is like nuclear charge is increasing. So the outermost electron or valence electron, it will be more attracted by the nucleus. Because of that reason, the atomic size it decreases. Now metallic atom, so you can explain all the rest based on the atomic size. If metallic in case of maximum atomic size, or if you are going down a group, atomic size increases, so metallic atom also increases. Now, if you are moving across a period, atomic size decreases, so metallic atom decreases. So non-metallic atom, it is opposite of atomic size. So if you are moving down a group, non-metallic atom, it decreases because atomic size is increasing. Non-metallic atom, it is having opposite trend of atomic size. So similarly, here it is decreasing, so increases. Now ionization enthalpy or ionization energy. If we are having if the size is increasing down a group, it means that the electrons can be easily removed by giving little amount of energy. So ionization enthalpy, it decreases. That means very little amount of energy is required. So with less energy or with less ionization energy, we can remove. So when we are moving down a group, ionization energy decreases. So when we are moving across a period, atomic size decreases. So in other words, it will be hard to remove the electrons, or in other words, we are supposed to give high amount of energy to remove the electrons from the outermost shell. So here ionization energy increases. Next one is electron affinity or electron gain enthalpy. So as we remember, when moving down a group, atomic size, it is increasing. So at electron affinity, it will be having opposite effect. So electron affinity, it decreases down a group. Okay. So if you are moving across a period, electron affinity is maximum on the top right corner, so it is supposed to increase here. The last one is electron negativity that we have discussed here. When we are moving down a group, electron negativity decreases. When we are moving across a period, it increases. So if you know this table, you can answer the most important question, that is what happened to the periodic table, periodic trend when we are moving across a period or down a group, and the reason behind it. If they are asking about the reason, you are supposed to explain based on atomic size. Try to explain based on the atomic size first. If they are asking about the atomic size, you are supposed to explain based on the nuclear charge. And also one more thing, if they are asking about down a group, about the atomic size, what happened to the atomic size if you are moving down a group, don't forget to write about the increasing shell, that effect being dominant over the nuclear charge. Okay. Other than these 6 periodic trends, there are 2 other periodic trends that is mentioned in the textbook. It is actually not necessary, but it is usually seen in almost all the textbook. It was, until now I haven't seen a board paper with about this part. Anyway, this periodic trend that I am going to discuss now, just go through it. It is not necessary because it is not a proper trend. Okay. Now, the first one, it is a chemical reactivity. It is not there in the syllabus, but just go through that in the textbook. So chemical reactivity, if you are mentioning, you have to, if you are going across a period, that means we have to consider all the groups. Last year you have studied about some groups, especially alkali metals, alkaline earth metals, halogens and noble gases. Okay, so as you remember, the properties of alkali metals and alkaline earth metal, they are highly reactive metals. So similarly, you have studied something about halogens. They are highly reactive non-metals. So we are having, on the left side we are having highly reactive metal, and here highly reactive non-metal. So what happened in between? What happened to the reactivity in between? So it is likewise on the left hand side, the metals which are highly reactive, then we will get the metals which are less reactive. If we go further, we will get metalloids which are not that much reactive, again less reactive non-metal, again it goes to highly reactive non-metal. So based on reactivity, you can draw a curve, it will be likewise. So no, it is just the opposite. Okay, first it is highly reactive, then it will reduce its reactivity, then we will get again more reactive elements. So if you are going across a period, this is a periodic trend in chemical reactivity. It will decrease its reactivity first. After a particular amount of after passing through certain elements, it will again increase. So reactivity, it will decrease first, because the alkali and alkaline earth metals, they are highly reactive. Then from them we will get the transition metals which are comparatively less reactive. Later it will increase again to most reactive non-metals like halogens. Okay, this is about the chemical reactivity. If you are going across a period, if you are going down a group, in going down a group, in case of metals, the reactivity increases. So you remember metallic character, right? So if you are going down a group, metallic character increases, or in other words, ability of a metal to lose electron will increase, or in other words, that metal will become more reactive if you are going down a group. So in case of non-metal, if you are in case of non-metallic character, if you are going down a group, non-metallic character decreases. In other words, if you are going down a group, the non-metal, it won't be ready to accept the electron, so non-metallic character, it decreases, or in other words, reactivity of non-metal, it will decrease down a group. So you can see the periodic table, left hand side it is metal. So if you are going down a group in left side, the metallic, the chemical reactivity of that metals, it will increase. But if you are taking it from the right hand side, they are the non-metals. When we are moving down a group, the chemical reactivity decreases. Okay, the next one, it is the physical properties like melting point, boiling point, and density. I think it is totally irrelevant. Just I'll be going through melting point and boiling point. In case of metals, if you are going down a group, melting point and boiling point decreases. If you are going down a group for non-metals, the melting point and boiling point, it increases. So this is the trend for melting point and boiling point for metals and non-metals. Just in case if you are going across a period, first it will increase, then it will decrease. It is just the opposite of the case before. First the melting point and boiling point, it will increase to a maximum point, then it will start to decrease. Now in case of density, it normally increases down a group, because atomic mass of each element, it is increasing when we are going down a group. In case of going across a period, we cannot say a correct value, because the size changes, the size is decreasing even though the mass is increasing. So we cannot predict a proper periodic trend for density when we are going across a period. On the first class, I have told whatever periodic trend that I am discussing, I am talking about that periodic trends excluding just one group from the periodic table, and that was noble gases. Now it is time for us to discuss about the noble gases. So noble gas, it is not following the trend properly in most of the cases. So you just have to consider the noble gases while we are discussing about just two trends. The first one is atomic size and the next one is ionization potential. The other trends, the metallic character, non-metallic character of noble gases, it is zero, because noble gas, it is having stable electronic configuration. It is not having a tendency to absorb the electron or donate an electron. So it is not having a tendency of a metal or non-metal. In other words, their metallic character or non-metallic character, it is supposed to be zero. Now, electron affinity. Electron affinity is the energy that is released outside when we are adding one more electron to the outermost shell of an atom. In case of noble gases, they are already stable, so it is not easy to add one more electron to the outermost shell. There is one more problem. In most of the cases, there is no new outermost shell, because in most of the cases, not all, in most of the cases, some of the cases, noble gases, they are having complete shell, complete electron in all the shells. In other cases, it will be less stable, very much less stable, if we are adding one more electron to the outermost shell. So it is not easily possible. So their electron affinity of all the noble gases, it is also considered as zero. Similarly, electron negativity for noble gases, since they don't form the compounds easily, they do form compounds under certain conditions, but normally it is not possible. So electronegativity of noble gases, they are also considered as zero. So out of all the periodic trends, metallic character, non-metallic character, electron affinity, electron negativity, this fourth trend for noble gases, it is zero, or there is no trend for the noble gases in these four cases. Now the later two, atomic size and ionization enthalpy, we are going to discuss the trends of noble gases based on atomic size and ionization enthalpy. Okay, the first one is atomic size. As you remember, if you are going from left to right in a periodic table, this is what that is going to happen. Okay, so if you are moving from left to right in a periodic table, the size of the atom, it is supposed to be decreasing. Okay, suppose you have to consider, suppose this is oxygen. Okay, now after oxygen we are having fluorine. Now the next one is neon. So according to the periodic trend, this neon, it is supposed to have a size that is lesser than fluorine, but in the actual case, it is likewise. Neon, it is having little bit size more than fluorine. Okay. So why noble gas is having this special property? Why it is having a size little bit larger than the halogens? It is not larger than the oxygen, it is just little bit larger than the halogens. The size of noble gases, they are, in some cases they are almost same as halogens, the adjacent halogens, or in other cases they are little bit larger than the halogen. Why it is so? So in case, what is the reason for the periodic trend in atomic size? When we are moving from left to right on a periodic table, nuclear charge increases, so electrons in the outermost shell, it is attracted more powerfully by the nucleus, because nuclear charge is increasing, so the size will decrease. So here also it is happening. Why the size of noble gases is increasing instead of decreasing? So there is one new effect, and that is due to the complete 8 electron in the outermost shell. So what happens if there is 8 electron in the outermost shell? Can just analyze from the diagram. In case of neon, it is having in case of neon, it is having 2-8 configuration. So just before we have discussed, if you are going down a curve, the atomic size increases. That is due to the repulsion between the electrons in the outermost shell and the inner shell, or a new shell is added to electron. The new electrons in the new shell, it cannot come closer towards the inner shell because of the repulsion from the electrons in the inner shell. So here it is a different case scenario. It is not due to the repulsion between the electrons from the inner shell and outer shell. It is due to the repulsion of electron between the same shell. Electrons that are present in the same shell, or in other words, we can simply call as inter-electron repulsion. Okay, so noble gases are the only elements with 8 electrons in the outermost shell. So in that case, what happens is they are having maximum number of electrons in the outermost shell. Because of that reason, the inter-electron repulsion in noble gases is maximum compared to all the rest of elements in the same period. So because of that reason, because of the repulsion between all the electrons in the same shell, this electron, they will try to extend their area, or they will try to stand apart from each other. So because of this repulsion, even though the nuclear charge is increasing, because of this repulsion, the size of noble gases, it increases little bit. It is not a high increase, it increases slightly. So in some cases, as I have told before, in some cases the increase in size, it is almost equal to halogens. In only very few cases, it is having size greater than that of halogens. Now you just need to go for one another example, that is helium. So helium is having little bit problem. Okay, so here helium, it is also having maximum number of electrons in the outermost shell. The maximum number of shell for helium is 1, and that is a K shell. It could accommodate only 2 electrons, and helium is having the maximum 2 electrons. But still, the inter-electron repulsion in case of helium, it is very less. Okay, so if you are considering the case of neon and helium, there is inter-electron repulsion between every 8 electron in the valence shell of neon. But in case of helium, it is not so possible. So helium, it is having an exception from inter-electron repulsion in case of all the noble gases. So all the rest of noble gases, it will be having little bit larger size compared to the actual size it is supposed to have based on the periodic trend. Okay, so only exception is helium. It obeys the periodic trend. So helium, it is in the first period, so there are only 2 elements in the first period, hydrogen and helium. So as according to the periodic trend, if you are moving from left to right, the atomic size is supposed to be decreased. So size of helium, it is smaller than the size of hydrogen. Okay, so other than helium, if you are checking any other noble gases, if you check it, compare it with halogens or oxygen family elements, the size of noble gases, it will be little bit larger than what it is supposed to be. Okay. Now we are going to discuss the next periodic trend of noble gases, that is ionization potential. So ionization potential or ionization energy, it is a minimum amount of energy that is required to remove the most loosely bound electron from the valence shell of an isolated gaseous atom in its ground state. So if you are taking the noble gases, so as we discussed before, noble gases, it is not easy to remove the electrons from the noble gases because they are already stable, they don't want to lose their electron. But still, if we are giving very high amount of energy, when we are giving very high amount of energy, the noble gases, even they can donate electron. It is true. So, but the problem is this: it requires very high amount of energy. So, in case of noble gases, since they are already stable, if you are removing the electron, since they need very high energy to remove the electrons from the outermost shell, the ionization enthalpy of the noble gases, they are very much higher compared to all the elements in the periodic table. In other words, if you are considering the first element in the first okay, suppose we consider the first element in the periodic table in any of the periods. If you are comparing the ionization enthalpy of the noble gas with the same element, it will be almost double or more than that. Okay, that much difference will be the in case of the ionization energy or ionization enthalpy for noble gases. So if you are asked a question, which one of the following elements is having the maximum ionization energy, if there is a noble gas, the noble gas will be the correct answer. So as you have studied, if you are going down a group, ionization energy or ionization enthalpy, it decreases. So the noble gas with maximum ionization enthalpy, it is helium. So helium will be having the maximum ionization enthalpy. If you are going down, the ionization enthalpy, it will decrease. Okay. Okay, just consider one of this atom, nucleus, 2 shells and 8 electrons. I think, okay, oxygen. Now, suppose I am going to remove one electron from this element. Okay. Okay, I will write the number of proton and neutron also. 8 proton, 8 neutron. I remove one electron from here. Okay, so after removing one electron from this atom, what is it now? If you remove one electron, it will become a cation. Okay, so cations are supposed to have a positive charge. So what is the process that I have done? I am removing an electron from the valence shell. So it is undergoing ionization. Okay, so I have converted a normal atom into an ion. So after removal, so suppose I have given a particular amount of energy to remove this process. That amount of energy will be the ionization enthalpy or ionization energy of this particular atom. Now, if I want to remove one more electron from the same cation, what will happen? That is the question. So the question is likewise, I have removed one electron from the outermost shell of a particular atom. If I remove the next electron from the same atom, will it require less energy or more energy? Less ionization energy or more ionization energy? So if you are looking at the current state after removing one electron, it is already a cation, or in other words, it is a species with a positive charge, and we want to remove a negative charge from a positive charge. It is not easy. Or in other words, you can tell it by the nuclear charge also. Here there are 8 positive charges. Nuclear charge is having, it is based on the 8 proton that is inside the nucleus, and total number of electrons around the nucleus, it is 7. So 8 8 proton, 7 electron. So the nucleus will attract all the other electron more properly. So to remove the next electron, we need much more energy compared to the previous one. So definitely, if we remove the first electron, if after removing the first electron, the energy that we energy absorbed was supposed to be IE1. So the second ionization energy after removing the second electron, it will be IE2. So there is no doubt, always the second ionization enthalpy. That means removing the second electron consecutively from the same atom, it will require more energy compared to when we are removing the first electron. So IE1, the first ionization enthalpy, it will be lesser compared to the second ionization enthalpy, or second ionization enthalpy, it will be always greater than the first ionization enthalpy. Now, what will happen if we want to remove one more electron? That means it is ionization enthalpy 3, IE3. So it will be greater than our ionization enthalpy 2, or in other words, ionization enthalpy 1 will be smaller than ionization enthalpy 2, which is smaller than ionization enthalpy 3. Or in other words, ionization, the maximum number of, if we are removing the maximum number of electron from a particular atom, the energy required to remove the last electron, it will be the maximum. Okay, so that is about the ionization enthalpy that I have told that I will take later. Now, what happened to the size of an atom when it is converted to a anion or cation? Okay, suppose we are having, suppose I have taken the same oxygen atom, 8 proton, 8 neutron, 2, and I have given very large amount of energy to remove one electron from oxygen, outermost shell of oxygen atom. So after removing this one electron, now it is having 8 proton and 7 neutrons, 7 electron. Okay, so 8 positive charge, 7 negative charge. So it is like here, what happens here is the nuclear charge, it is much more compared to all the negative charge that is around. So in other words, all the electrons that is around the nucleus, it will be having more powerful nuclear force of attraction. Suppose oxygen atom was likewise before removing the one electron from the outermost shell. So after removing the electron, the size of the oxygen atom, it will decrease. The reason is, after removing one negative charge, the total positive charge inside the cation, it is increased because the negative charge is removed from the atom. So because of that reason, the outermost shell of electron, it will be more attracted towards the nucleus. So the size of the atom, it decreases. Now, just now we talked about removing one electron from the outermost shell of an atom. Now what if we added an electron? Okay. So here what happens is this: total number of proton is 8, total number of electron is 9. Earlier, 8 protons used to attract 8 electron. Now it had to attract one more electron. So the total amount of nuclear charge in the valence shell, it is decreasing because the extra electron that is added to the outermost shell, it will be taking in a certain amount of nuclear charges. So suppose this was the size of the oxygen atom. After absorbing or after gaining one more electron, the size of the oxygen atom, it is supposed to increase a little bit. Okay, I hope you understand. Okay, there is little bit mention about bridge elements that you are studied in the smaller classes. So, bridge elements, they are the elements which are having some. Okay, the last part of this chapter, it is about bridge elements that you are studying in your lower classes. So, as you remember, if you are going across a period, the atomic size is decreasing, right? Okay, I will draw it once again, it will be more larger. Okay, so if you are going from left to right in a periodic table, atomic size increases. If you are going down again, atomic size it will increase, right? So what happens if you are going to the left to right in the period which is just below? So if you are going from left to right, again the atomic size is supposed to decrease. So it will be like this. Okay, so okay, it will be likewise. So is there any similarity between both? For example, if I remove this, are you finding any similarity? It is just like this one is having similar size with the next bridge element. This to this to this, and this to this. So these are the bridge elements. Okay, so drawing the previous one back. So bridge elements, they are the elements which are present in the next period, not exactly, but in a diagonal manner. So for example, if you are considering sodium, the bridge element to the sodium is calcium. Okay, so here suppose this is sodium, so this is potassium, here is our calcium. So sodium and calcium, they are supposed to have almost similar sizes, so they can be considered as a bridge element. So what happens if two elements are having similar size? So just now we have discussed almost some 5 periodic trends, and all the explanation of these periodic trends was given based on atomic size and nuclear charges. So if they are having almost same atomic size, that means they are having many chemical properties which are similar. So those bridge elements which are having which are the reason behind that, it is due to same atomic size, they are having many chemical and physical properties similar. Such elements are called bridge elements. There are many examples. Okay, these are the examples of some of other bridge elements. Lithium and magnesium, it is one pair of bridge element. Beryllium and aluminum is another example. Boron and silicon, they are the last, not last, there are more. These are the, some of the examples that is given in the textbook. So these elements, they are having similar size. Because of that reason, they are having some similar chemical properties. And that's all for today. But other than that, I have given some homeworks for you in the next teach next app. So please go through that. It is of the first chapter. I think the last date for submission of the homework, it will be on 29th. So try to do it before that. I haven't given an option for late submission. So after 29th, you won't be able to complete your work. Now, other than that, this chapter is over. We are supposed to discuss a little bit of the problem, and that's all. So the next class, we'll be starting our next chapter. The next chapter is chemical bonding. So last year you have studied something about chemical, atomic structure and chemical bonding. Next class you have studied a chapter about atomic structure and chemical bonding. This year there is only chemical bonding. Atomic structure and chemical bonding both are supposed to be together. So this year, since it is not there, you are supposed to go through the atomic structure by yourself. Chemical bonding, we will be starting directly to the chemical bonding on the next class. So even though we are studying the chemical bonding, whatever we have studied in the 9th class, 80% of the same chapter is again repeated in the next chapter, chemical bonding. So you go through the entire chapter. I think it was some 4th chapter or something. So go through the atomic structure and chemical bonding from the 9th class, study it thoroughly. Next class will be the continuation of that part. And also one more thing, study first 18 elements. I suggest you to study up to first 20 elements. You are not just supposed to study their atomic number, study it just by atomic number wise. You are supposed to study the group also. At least study the first 4 elements from first, second, that is alkali metal, alkaline earth metal, halogen and noble gases. First 4 elements of alkali metal, alkaline earth metal, halogens and noble gases. Other than that, study first 20 elements. Okay. Try to draw the atomic structure of all the first 20 elements. I think we have done the same in the 9th class. That will be a good exercise for the upcoming chapter. That's all. Thank you.